So how do we determine solubility product using conductivity measurements? This is the other experiment. I told you that this one can work for any sparingly soluble electrolyte. And it's a common procedure that you're going to see me modifying for any electrolyte. I'm still using the magnesium hydroxide, and we shall begin the usual way. We shall still say an excess of solid magnesium hydroxide is done what? Is dissolved in a given volume of distilled water. In a container. The mixture is shaken for some time, as we have already seen. Mixture is shaken for some time and allowed to settle at a given temperature. At a given temperature to attain equilibrium. The mixture is then filtered. To obtain a saturated solution of magnesium hydroxide. As filtrate. So in all experiments, this is the starting part. Things begin to change after this point, depending on which method you're going to use. So if it was direct titration, then you could be doing titration as the next point here. But when we are using conductivity measurements, the procedure slightly changes here. So what are we going to do next? We are going to say the electrolytic conductivity. The electrolytic conductivity of the saturated solution. We are calling it K. That's normally the symbol that denotes electric conductivity, whose units are per ohm per centimeter, is measured using a conductivity meter. So you measure the electric conductivity of the saturated solution using a conductivity meter. I may not be able to show you how a conductivity meter looks like here, but when you go back to school, check in the school lab, ask for what a conductivity meter is, you'll see how it looks. It's used to measure electric conductivity of any given solution. Then you also get the electrolytic conductivity of water at the same temperature from books. This one is read from books. The electrolytic conductivity of water at the same temperature. Carried out the experiment is read from the books. Is read from the books. This one is normally denoted as K water with units still the same units as we have seen, per ohm per centimeter. Now, after measuring the electrical conductivity of saturated solution from a conductivity meter and also obtaining the electrolytic conductivity of water from the books, remember our salts we have been using our electrolyte, I mean, is magnesium hydroxide. It has magnesium ions in it and hydroxide ions in it. We are now remaining with one other last mathematical data to carry out the treatment of results. So we also read the molar conductivities of magnesium ions and hydroxide ions are read from the tables. There are always books or data tables that have these values. Now, how do we treat our results here? After doing that, we go to the treatment of results. Remember, we have got the K solution, electrical conductivity of the solution from a conductivity meter. Also obtained the electrical conductivity of water from the books. This electrical conductivity of this electrolytic conductivity of the solution, when you subtract off that of water, remember this is a saturated solution. That saturated solution, there is magnesium hydroxide, there is also water. So you need to obtain the electrical conductivity of magnesium hydroxide alone using these two values here. And that's what we are going to do here. We shall get electrical conductivity of magnesium hydroxide as the electrolytic conductivity of the solution minus the electric conductivity of water. Are we together?
Yes, teacher.
Then you also get the molar conductivity of calcium hydroxide at infinite dilution. Okay? Those words you write them, I'm not writing them to save time. You also get the molar conductivity of magnesium hydroxide at infinite dilution. This one is got as molar conductivity of magnesium ions at infinite dilution plus twice molar conductivity of hydroxide ions at infinite dilution. Why do I multiply the molar conductivity of hydroxide ions at infinite dilution by 2? Because in the formula of magnesium hydroxide, there are 2 hydroxide ions. We also get that value. And then we take an assumption that molar conductivity at infinite dilution of magnesium hydroxide is equal to molar conductivity at a given concentration of magnesium hydroxide, where this one is molar conductivity at a given concentration of magnesium hydroxide. But from mathematics, we know that molar conductivity at a given concentration of magnesium hydroxide is always equal to 1,000 electric conductivity of the compound we are looking at, which is magnesium hydroxide, over the concentration or solubility. C is concentration or solubility in moles per liter. So by this expression, remember we have this from here. After taking this assumption, we have this from here. We can now get the solubility of magnesium hydroxide in moles per liter, which we can use to do our treatment of results as we have already seen. So if this one in solution gives us magnesium ions and 2 hydroxide ions, in our treatment of results as we have previously seen, this has been got, its concentration is C. Its molar concentration, we have just got it as C, moles per liter. So I'll not go through the details, but according to molar concentration, the molar concentration of magnesium ion is also BC, moles per liter. And the molar concentration of hydroxide ions will be 2C. Are we together?
Yes, teacher.
Such that our KSP is equal to concentration of magnesium ions, concentration of hydroxide ions, which is equal to C into 2C squared which gives us 4C cubed moles cubed -6 as our solubility product. Now, having got those two experiments, you can use any of them to determine solubility product of any other compound.